Hi, welcome. Ah. Okay, so the background of this talk is, which might be interesting to you because we are in Norway, is because I worked for the last 3 or 4 years with the Norwegian government, especially the healthcare sector, because they were basically redoing their infrastructure from, more traditional style of security to an OAuth and OpenID Connect based system. So, part of that ongoing project, which is a huge project, as you can imagine, is, raising security awareness for all the people that work or, that touch these systems. So one deliverable, if you like, was to create a training course that, talks about OpenID Connect and OAuth security best practices. And this is, think of it as like the 60-minute version of that. So in some way, this talk is sponsored by Norway. Okay. Yeah. I have to warn you though, yeah. When you start looking into these things, you have to deal with documents that look like this. Okay. So that's a Korea font. The font stops here, right? It's all serious now. Luckily, they have a PDF document for you, a PDF version, right? So if that's too harsh for your eyes, you can try this one. Oh no, you can't. Yeah. Yeah. The other thing you have probably have to get used to is things like this, ASCII art. Okay, so I really hope someone has a tool for that. They don't have to, like space. And the reason why these documents look like this is basically goes all the way back, because it's the IETF, right? I mean, they made the internet, right? So it had to work on the very first browser that was ever in existence. Do you remember what it was? The browser called Lynx. It looks like this, right? So when I, what's the key combination here? Control G. No. Anyways, if you would open up that same URL, it would look exactly like what you just seen in Chrome. Okay, and that's 30 years of backwards compatibility. And they even had dark mode, right, by then. So, Okay, good. My name is Dominick, and I'm working in that space for a very long time. I am the author of one of the OpenID Connect certified OpenID and OAuth implementations called Identity Server. So yeah, so I'm pretty much, have the luxury, and some people are not clear what luxury means in this case, of working full time with these things, okay? I uploaded the slide deck to here, to speakerdeck.com/leastprivilege. So if you want to have that slide deck, you can just download it right now if you want, or after the talk. The rough plan is this: give you a little bit of overview of what security guidance is out there today. Help you with categorizing what applies to you, what does not apply to you, where does it fit into the big picture, so to speak. Then I picked out a couple of interesting use cases. Yeah, some more common, some maybe uncommon ones. Yeah. They are by far not all of the use cases that are described in these documents. So the call to action would be afterwards, start downloading these things. They're tiny, they're just text files. So no worries, yeah. After that, I want to talk a little bit about what's happening with OAuth in the future, because there is some interesting thing going on right now, which will impact all of us. Okay. Let's give you some context first, okay? So the very first web-based protocol, you would say, was SAML 2P. Yeah, it basically invented the pattern that we all use today, which is goes to some external provider, get a post back with some stuff, okay? And that's basically how they all work: OpenID Connect, OAuth, WS Federation, SAML, and so on. So they basically invented this pattern, if you like. Yeah. SAML was an authentication protocol. It didn't solve the API access problem because, well, guess what? There were no APIs in 2005, right? So OAuth was invented to, in addition, solve the token-based API access problem. But again, OAuth 1.0 is pretty old. It used some old technology. It was hard to use, actually, lots of crypto involved. So in 2012, they came up with OAuth 2.0, and they made a simplified version of OAuth. Not everybody was happy with that, to be honest, because the crypto was gone to make it easier, but security, you could say, was lower than in OAuth 1.0. If you Google for it, there was the original spec author of the OAuth spec, he left because he was so angry with the IETF that they watered down his little protocol that he created in the first place. And I think he had good points here. One of the results of him being so angry is he demanded, you must publish a threat model with that, right? So, certain things you can do in OAuth are insecure, and the spec doesn't give you any guidance if you should do it like this or like that, or what's the right way of doing it, right? So they created this threat model and security considerations document. But imagine this was written at the same time the spec was written, so all that's in there is what they knew by the time, right? And again, since OAuth wasn't not really applied to practical scenarios by the time, they also couldn't give you like really actionable guidance. They could just point out, that's a potential problem, that's a potential problem, and that's a potential problem, yeah? But not telling you how to fix it exactly, okay? So, that thing was out there for a while, and then new specs got created, yeah? And that's just a fraction of the specs. Actually, someone counted all the pages of these specs recently, and he said it's double the size of War and Peace, which I think is a pretty big book, right? So you decide what's more exciting to read. But the point was this. Many people said, like, okay, the threat model is old. The threat model doesn't give us any guidance. Can we produce new documents on top that actually give a developer real guidance in what to do, okay? And not just what to potentially do, yeah? And that's what they call the security, or the best current practices, BCPs, yeah? There is a reason why the word current is in there, right? Because the older they get, the less current they are. So they try to capture what happens at this point in time and give you concrete guidance on how to implement things. The first of them was for native applications, yeah, mobile apps, yeah, because that was a big thing. People started using OAuth for that. How do you do it right? As we speak, there are two other very important BCPs being worked on. One is called the OAuth 2.0 Security Topics BCP, which you can think of as an update to the threat model, okay? So what have we learned in the last 8 years, so to speak, how OAuth was applied, and what, from our point of view, are now the current mitigation techniques, what are the attacks, and so on. And a very, very important other one is the OAuth for browser-based apps, BCP, right? Because, as we all know, browsers are the hardest thing to secure. You need a lot of guidance there. Okay, so basically the talk is about the red things here. Yeah? So if you want to put that into perspective, the threat model was the mother of all BCPs, if you like. Then this one is a very general one, which talks about OAuth in general. And then on top, you see the two which talk about very specific application scenarios. And just recently, two new ones popped up, which are not essential for our discussion, but they belong to that bigger picture. One is how to use JSON Web Tokens securely in OAuth, and then how to use JSON Web Tokens specifically for access tokens, because OAuth never specified the token format, yeah? Cool. So that's how a typical OAuth-based system looks like, or OpenID Connect-based system looks like. We have front ends, we have back ends for back ends, right? We have users, we have clients, we have authentication, we have API access, and typically a thing called the security token service is what coordinates all these things, like a traffic cop, if you like, that hands out the tokens, makes the access checks, and much more, okay? To simplify that, how OAuth really works is like this. You have something called a resource owner, which is, in my world, a user, which is, I think, a better word for it. You have a client, which is an application. You have a resource server, which is an API, typically. And you have this thing called the authorization server, yeah? And regardless how you use OAuth, it will always work like this. You first go to the authorization server, you get a token, and then you use that token to access the resource. There are a couple of flavors, but in essence, that's how it works. Now, the very first thing to think about is, when you're building such a system, who are my attackers, right? So if you want to secure the system, you need to understand who is attacking them. So, and by the way, I used the cheesiest symbol for an attacker that I could find on the internet, yeah? Forgive me, I guess. The very first type of attack you have to think about is, what if my infrastructure is compromised? Okay, so somebody can read or modify traffic, or maybe can even, tamper with my DNS infrastructure. Yeah, so one thing to think about is, okay, why can they read and modify traffic? Because are you using TLS? TLS is mandatory for OAuth, okay? So you should never ever do anything, yeah, without TLS, yeah? But if your infrastructure is still compromised and they can still read and modify traffic even over TLS, you have a huge problem that we can't solve as OAuth implementers. That's a whole nother world of problems. So we have to rely on that being intact, okay? The next type of attack could be the compromise of an endpoint itself. Yeah, what if the client is compromised? What if the authorization server is compromised? What if the resource server is compromised? Yeah, again, from an OAuth implementer point of view, or from a protocol point of view, there's not a lot you can do about this. You have to find out, why are these things compromised? Yeah, you can't trust them. This will be an insecure system. Let's move on to something else, which I think, in my mind, is the battleground of the future. Yeah, they don't have to compromise anything. They add stuff to your system. For example, a rogue authorization server, or a rogue client, or a rogue resource server. And maybe they even manage to register their rogue resource server with the legitimate authorization server. Or they trick the legitimate client into using the rogue authorization server. And you can imagine any permutation of that being very problematic. Okay, that's what we see today for very targeted attacks, yeah, where someone specifically targets a certain application or company, right, where maybe the implementation is really good, but this might give you a lot of avenue for confusion and unforeseen vulnerabilities in your system, okay? I'm going to show you an example of that later. Sadly, to be honest, the 90% types of OAuth attacks we see are implementation flaws, right? Somebody has written an OAuth server, somebody has written an OAuth client, they didn't follow the best practices, and stuff goes wrong. So for example, the idea is that an attacker can read but not modify the contents of the authorization request and the response, okay? That does not necessarily need network access. This might only mean, right, maybe your application has a bug and you have an open redirector in there. Maybe somebody can redirect the intercept the redirection on a mobile device. Maybe you are leaking network packages like in log files or in proxies or in the browser history. All of these things, yeah? These are by far the most common attacks we see. And the good news is they can all be fixed by writing the right code. Okay? Good. So, the elephant in the room, that's what the whole OAuth security discussion got started again after being dormant for a while, was this guy, Thorsten Lodderstedt, a well-respected colleague of mine, who wrote this blog post. You should not use the OAuth implicit grant. And you might know that, right? The OAuth implicit grant was, by the time, the recommendation for implementing browser-based applications, yeah? So he wrote this blog post, and he used these words here. This might, for example, result in an attacker accessing your health records or initiating a payment from your bank account. And you could only imagine what happened the next day. I got emails from customers all over the place saying, hey, have you read this? There's a new vulnerability in OAuth. And I said, no, that's not true. It's not a new vulnerability. It's a known weakness of this specific flow that you can mitigate if you're writing the right code. The problem is many companies don't write the right code, and the real problem with implicit flow is it's error prone. Okay? So just to recap that, what's the implicit flow? The implicit flow was invented to give JavaScript-based applications an easy way to request tokens from an authorization server, given that cross-origin AJAX calls did not exist by the time. Okay, 2012, there was no cross-origin AJAX calls, so they had to find something that is purely working on URLs, right? So you asked this guy for a token, you get back that token on the URL, okay? And that is error-prone because, as I said, this URL ends up in log files, this URL ends up in the browser history, and browser behavior has changed as how a hash fragment has been treated, for example, and imagine referrer headers, and it is troublesome. Okay? It's not that a new vulnerability has been discovered. This was always the case from day one. And to be honest, the threat model pointed this out explicitly, but I guess no one read the threat model. Yeah? So, long story short, now today we have CORS, right? The cross-origin resource sharing, which allows us to do cross-origin AJAX calls, which means we can use a different flow that uses AJAX, which does not have to use URLs. So implicit flow will be deprecated, okay? No more implicit flow. It's not needed anymore, right? It's being created out of a need, but it's not needed anymore. And as I said, it's not inherently insecure. It's just error-prone to implement. So we want to get rid of this, okay? That's action item number 1. While we are at deprecating stuff, no more password grant. Okay, the password grant was this very, very old flow in OAuth where you collect the credentials of the user in the front end and then send them to a token service and you get back a token. This is bad practice all over. Okay, you are encouraging users to type in passwords in different places. Research has shown the more often a user types in the password, the more prone they are to phishing attacks, for example. And this is not compatible with any of the modern authentication techniques like FIDO, 2FA, Federation, and so on. It's still widely in use, mostly for legacy or for other reasons that typically only product owners know. Again, this is going to be deprecated. That's action item number 2. Don't use it. So, which is quite nice. That's good. We improve by reduction, so to speak. Yeah. I'm doing these OAuth trainings for a long time, and that was kind of like the decision matrix at the end of a training, right? If you're doing this, use this flow. If you're doing this, use this or that or that. If you're doing this, use this or this or that. Yeah. Now I have crossed out the deprecated ones, and it turns out, as I'll show you in a second, when you basically apply common sense here, all we need is 2 flows. Right? Because all we have are 2 fundamental types of applications. One are machine-to-machine. There is the OAuth client credential flow for that. And the other type is interactive applications, where a human being is using it. And for all the other cases, we now use the good old, actually the mother of all flows in OAuth, called the authorization code flow. The mother of all flows has a problem. That's what we're going to fix with a thing called PKCE. I'm going to show you in a second what that is. But ultimately speaking, you only need to choose between one of the 2. Your developers only need to learn these 2, right? And your architect only need to understand these 2. That's it. And that's much better than a year ago. Good. So let's start with machine-to-machine communication. As I said, the way this works is the client goes to the authorization server, authenticates with the authorization server, asks for an access token for certain resources, gets back an access token if he's allowed to do that, uses the access token, that's it. Okay? So what is there to harden? Good question. The first thing, I guess, that still is around a lot is how do the clients authenticate with the server? Obviously, the easiest way, it seems at least, are shared secrets, right? So you have a secret here, you have a secret there. If someone can prove that secret is known, then he's authenticated. Shared secrets are not really secrets because they are shared. So don't try to avoid them, okay? I mean, they are the easiest thing today, but in practice, when you implement this, configuration management is really hard, right? Where do you store them? Where do you store them not in clear text? How do you store them that they don't leak to your version control system or other things? It's if you use them, yeah, use high entropy secrets like GUIDs or random numbers or something like this. Don't even try to, it's a password, but it's a password for machines. They don't need to be memorable, okay? They can be really long and really hard, yeah? If you are storing them, store them non-reversibly, right? If somebody compromises the database of the authorization server, they shouldn't be presented with a menu of secrets. Yeah, what they should see is hashes of secrets, yeah? Since these secrets have high entropies, you don't need to apply any key byte stretching, for example. It's a GUID, hash the GUID, that's good. If you can move away from shared secrets, use asymmetric keys. The nice thing about asymmetric keys is, A, the server does not need to store any secret at all because all they store is the public key, right, and nothing else. They never go over the wire, so you can't intercept them on the network because all you're sending is a signature that has been done with the secret and not the secret itself, okay? And it has the nice side effect that it gives us more features, which is called sender constraining. And the most important, or the most common ways to do asymmetric keys these days is either basically creating a JSON Web Token, signing it with the secret, and using that as a client secret. Or you're using the transport, like mutual TLS, for example, so that the transport layer protocol will take care of these things, okay? The nice thing about TLS is that it gives us what we call sender-constrained tokens or proof of possession tokens, meaning if the client asks for a token over a mutual TLS connection, once the TLS cert has been validated, we can basically put the hash of that certificate into the access token itself via the CNF claim, it stands for confirmation. And then the client uses the same client certificate to talk to the APIs. The API receives the access token. It gets the thumbprint of the client certificate, can compare that thumbprint with the thumbprint in the access token, and then this was really the client that asked for the token in the first place. If an attacker steals that token, they can't use it because they don't have the private key. Okay? That is, I think for 2020, we should make sure that we are using this technique because it's easy to use and it's so much more secure. Okay, speaking of JSON Web Tokens. As I said, JSON Web Tokens have never been specified for OAuth, yeah? It was just a thing that happened because they were around, they are easy to use, they are widely deployed, there are so many client libraries that can deal with them. So people thought like, hey, JSON Web Tokens, yeah? Let's use them for everything, yeah? They seem to be a nice way to protect a JSON object, and they are. So JSON Web Tokens are used today for identity tokens in OpenID Connect, for access tokens in OAuth a lot, for logout tokens, for single sign-out. Security events is another spec that uses JSON Web Tokens. The funny thing is, once you start using them all over, they become a bit complicated because you can't really distinguish between them anymore. They all look the same, right? They have a header, and they have a payload, and they have a signature. Okay? So I'll give you one example. Here's the spec of the logout token validation, yeah? So they say like, yeah, validate the signature, that's fine. Validate that it contains a subclaim, and so on, that's fine. And then it says something like this. Verify the token does not contain a nonce. And why is that? Well, because if it would contain a nonce, it could be actually an identity token that someone tries to smuggle into your system saying, hey, here's a logout token, okay? Because, it's hard to distinguish between them. So a really very small thing that you should start using is called typed JSON Web Tokens. And the idea is that here you see that type header, that always said JOT. But now what you should do is you should introduce basically encode the purpose of the JSON Web Token into the JSON Web Token itself. So currently, the OAuth spec for JSON Web Token says use the value AT plus JWT. Okay, that tells the system this is a JSON Web Token, but it is also an access token because it has this well-known string in the type header. Okay, and what you should do is if you come up with your own JSON Web Tokens, invent a name for them, right? So that someone can't confuse one type with the other. I'm working on this thing called Identity Server. We start doing that now since, I think, 6 months. All of our access tokens look like this, okay? Just to make sure that when you're validating them, you can make sure it's actually an access token, it's not a logout token, it's not a security event, it's not an ID token, or whatever other things you come up with, okay? So that's also something you should do. Good. Let's switch gears to interactive applications. And they are browser-based, right? The browser is very powerful, right? It can show UI, it can follow redirects and so on, but the browser is also the most problematic part of the system because, well, it can show UI, it can follow redirects, right? Maybe to the wrong place, yeah? So be careful with that. But how does that flow work? Well, it's super simple, right? You have two channels. One is called the front channel, one is called the back channel. You first do the authorize request. You get presented with some UI on the server. The server replies with a so-called authorization code. And then the authorization code gets on a back channel communication redeemed and turned into access tokens, right? To redeem that access token, the client has to authenticate with the authorization server, and that makes the authorization code quite nice, right? Because if an attacker sits in your browser or on your network because you're at the airport and the Wi-Fi called free Wi-Fi was very attractive to you, yeah, who knows who runs that network, right? If they would steal that authorization code from you, they cannot redeem it without knowing the secret, okay? Only the client knows the secret, and that's the only party that can turn this code into a token, okay? Job done, right? We're good. Yeah, that is where most things go wrong, okay? And I'm just picking out this one because it's the most popular. Because, on this leg here, when the server responds back to the client application, that is a very sensitive operation, right? Because that's where you deliver the data, and that's called the redirect URI. And the spec says the redirect URI must be pre-registered with the client, and there must be an exact string matching between the redirect URI that was pre-registered and the one that's being used at runtime. That's what the spec says, but that's not what people do, apparently, yeah? So, for example, this here, I've seen this in the wild, yeah? Let's allow it on our side, but any subdomain, okay? So that actually happened to Electronic Arts last year. There was an attack called subdomain takeover. So basically the short story is somebody created a website on Azure. It was called something, azurewebsites.net, and they implemented the EA billing system on this. At some point they were ready, so they put a DNS entry into the ea.com domain. Billing.ea.com points now to Azure Websites. Fine, right? At some point, they moved the billing system to another domain. No one needed that Azure website anymore. They shut it down, but no one took away the DNS entry. So now all an attacker needs to do is scan your DNS, say, hey, you have this thing pointing to Azure, but on Azure there's nothing. So let's just register the Azure website again with the same name. And now suddenly you can run code under the EA domain, right? Billing.ea.com is now my server, because your DNS routes me there, okay? So yeah, very dangerous. This one here, I have seen in the wild as well, mysite.com/star. Any URL will do on that site. What they all have in common is you are extending the attack surface of the redirect, the callback URL, if you like, yeah? On that callback URL, sensitive stuff is being executed. You want to tie that down to a single place where your code is running, nothing else should run there, no Google Analytics, I've seen that too, no ad banners, I've seen that too. Only the code dealing with the callback should run on that specific URL and nothing else. If you do a star there, you can choose whatever you want, right? That is exactly what happened to Facebook, by the way, yeah? So Facebook allowed facebook.com/star as the callback URL. So someone was pretty clever, and he found out, well, let's handcraft a URL that says, facebook.com/my_Facebook_page, and send out these links, right? People clicked on the links, they came to Facebook, they logged on to Facebook, they ended up ultimately on his Facebook page. Okay, that's annoying, but is that dangerous? Yes, it is. Because what he did on his Facebook page, he posted a picture that came from a server that he controls. Okay? So now, what is the browser doing? He loads the page, he loads that evil.com image PNG, what does the browser put on the referrer header? The code, right? So that's how he basically leaked the Facebook authorization code to his log files. Yeah? So now you might think, yeah, but what's the problem? I need a client secret for that, right? That's what I just said. Yeah, maybe not. There's another interesting attack called authorization code injection. The idea is you steal an authorization code somehow, okay? Via one of the attacks, open redirector, leakage, whatever, I have stolen your authorization code, okay? So now I just go to the legitimate application, start the authentication process, and then I handcraft a URL to the callback endpoint that has the stolen code, right? So now what will the client application do? They will take the code and happily turn it into access tokens because they have the secret and I am now logged in as my victim to the application, right? So even if code requires a secret, at least for confidential clients, there is still an attack vector here if you can steal a code somehow, if it got leaked somehow, okay? So we thought code is the most secure mechanism. It turns out it's not. Well, but we can make it secure with something on top, which is called proof key for code exchange, or PKCE, as the cool kids say. Yeah? PKCE is a very simple extension to the authorization flow, and the idea is this. Before the client makes the redirect to the token service, he comes up with a random number, okay? Just some random number, and then he hashes that random number, and the random number is called a code verifier, and the hash of the random number is called the code challenge, okay? So now when we do the authorize request, we in addition send the hashed version of our secret to the server, right? We don't want to send the clear text version of it because the browser is considered insecure. So now the server stores that code challenge and comes back with the code, right? And now on the back channel communication, the client sends the clear text version of that secret, the code verifier. So now the server has the clear text version, he has the hashed version, so he can hash the clear text version, and if they match, you can prove that you are the client, the same client on the front channel as you are on the back channel. Okay? Now if somebody comes with a stolen code, this stolen code was requested using a different code verifier than the one that you can use because you don't know the secret of the client. Yeah, it's just in memory. So this will not work anymore. Okay? So long story short, I said earlier, use authorization code flow for all of your applications, but only if you use PKCE on top of it. Okay? So code plus PKCE is the requirement. And if you're doing ASP.NET Core, for example, starting with version 3.0, they always do PKCE, right? It took a bit of convincing them why this is useful, but we managed that. Starting with 3.3.0, they always send the code challenge and the code verifier. And then when you have a token service like Identity Server, you can basically go to every client, say require PKCE, require PKCE, require PKCE, and then you shut down this problem. Okay? Cool. Let's move on. We have so much content. As a summary, okay? These are the most actionable things. Always do exact matching of redirects, yeah? Don't do open redirectors. Sounds easier than it is, but do it. Callback pages should contain no third-party code, only your code. Use CSP for lockdown. Don't do inline JavaScript. Always use PKCE. We can skip the skate part. That is also interesting, but not as interesting because PKCE saves you from that. Also, that's a really nice, easy one to do. Shut down referrer headers. Yeah, you can have a referrer policy in your browser to tell the browser don't send referrer headers, and you close that potential problem as well. Yeah. Good. Let's show you some more advanced things. Yeah, which might make your head hurt. It definitely did with mine the first time I saw it. Yeah. It's called a mix-up attack. And the mix-up attack is a more advanced scenario. The idea is that you're having a client that trusts more than one authorization server, right? Think of a federation gateway scenario where you have, Google login and Facebook login and this and that. So yes, you're already in that scenario because your federation gateway is a client to more than one external authentication system, right? So now I told you the sophisticated attacks are the things where I can substitute stuff and confuse the client application somehow, and that's one of them. Yeah, it's called the mix-up attack, and it goes like this. The variant 1, by the way, makes the assumption that the attacker can somehow modify the traffic between the browser and the the authorization request, so to speak. Yeah, but yeah. We have two STSs, yeah? One is called the honest STS, which is the good one, and one is called the attacker STS, which is the bad one. So imagine that the user clicks the honest STS in the UI. I want to log in with this guy, or get a token. So he chooses that one. The attacker can on the fly change that to the attacker STS. Okay. So now the client thinks he wants to talk to the attacker STS. He stores the fact that this was the selected STS. He sends him 302 back to go to the attacker STS, and the attacker swaps it back out to the honest STS. Okay? So now the browser goes to the honest STS. The user authenticates, does his thing. The authorization server sends the code back. The code travels up to the client. Who is the client thinking is the right STS to exchange the code with the token? The attacker STS. Now suddenly the attacker STS has the authorization code and the client ID and the client secret, right? And all he has to do now is just do a backchannel call and redeem that with the honest STS. Does that make sense? Now you might say, there are a lot of assumptions here, right? And there are, okay? But this is not made up. This has happened. Okay, there are assumptions here. One is you trust more than one STS. Someone was able to smuggle in an attacker STS into your system. The attacker has access to the network somehow. Okay, that might be far-fetched for some of you. There's a different variation which does not require network access. Okay, it works a little bit different like this. So the idea is this: the user selects the attacker STS. For some reason, yeah, maybe you have some sort of self-service registration of your customer STS. Somebody posted an STS that looks very similar to the one you really want to do, right? You choose the wrong one. That's what happens. Yeah, you choose the wrong STS, then the client sends the user agent to the attacker STS. Yeah. Now, what the attacker STS is doing immediately is he turns around and forwards that call to the real STS, the honest STS. So you're seeing the right login page, everything. He changes on the way, he changes the client ID, he changes the redirect URI, and so on and so forth, okay? So now the honest STS thinks he just got a request from the client. So he will send the code back to the client. Where will the client send the code to now? To the attacker STS. Okay? So yeah. That's a bit more advanced, and I think it requires a very specialized attack for that. But as I said, this is not made up. Yeah? So, how can we protect against this? My best answer I have is use a good client-side framework. Okay? If you have written your own OAuth or OpenID Connect client library, make sure you do this. Use authorization server-specific redirect URIs. They shouldn't share them, right? Like one endpoint that handles all the callbacks, that's a bad idea. Store for each request the intended AS, and then on the way back, compare the intended AS with the redirect URI that belongs to the actual authorization server, okay? The good news is, if you're doing ASP.NET Core, they got you covered, okay? And to be honest, this countermeasure was done by Microsoft before the attack got published, so it's a bit like secure by accident, I think, but it works. So, in ASP.NET Core, every external provider must have a unique name and must use a unique callback URL, okay? So when you initiate the challenge to the external system, what they can do is they come up with a random number, they call that the correlation ID, and they encrypt and sign that random number and send it on the state parameter to the authorization server, okay? In the OAuth spec, it says that state parameter must be echoed back unchanged to the client. At the same time, what they do is they drop a cookie that is called correlation.authorization server name dot correlation ID, the random thing they just made up. Okay? So now when the response comes back from the authorization server, it's an AS-specific callback URL, right? And then they look at the state parameter, they unprotect that with their key, so they decrypt it and validate the signature, so no one has changed it. And then they get the correlation ID out of that, and they make sure that a cookie exists with this name correlation authorization server name dot correlation ID. And only if that exists, you know that really the request and the response, they belong together. Okay? As I said, if you're doing ASP.NET Core, that's built in. You don't need to worry. If you use something else, you need to check how they are doing it. If you wrote something yourself, you should double check, I guess. Yeah. Okay. Whew. Good. So let's turn our attention to a couple of different things. Public clients. Okay, so far we talked about what they call confidential clients in OAuth, which has a nice security property. They have client secrets because they are deployed to a trusted server or something like this. Yeah. With public clients, this assumption is not true. Public clients are things running in a browser, like JavaScript or a mobile app or a desktop app. They don't have secrets because what's the point? Where would you deploy that secret to, right? Certainly not in the source code. Yeah? So different rules apply here. So in the confidential world, we are used to having basically a one-to-one mapping between client and client ID, right? MVC1 and MVC2 and my front end and my back end and so on. With public clients, that's not true, right? Because you're creating a mobile app, my cool client, you deploy to the App Store, 5 million people download it, 5 million people will use the same client ID, right? That's just the way it is. Yeah? So in other words, you can't authenticate the client with public clients. It's just not possible. So let's have a look first at native clients. So the very first anti-pattern that gets pointed out by the native client's BCP is don't use native login dialogues, right? Again, I said it earlier, if you educate your users to type in the password in many different places, they are probably more prone to phishing attacks, so don't do that. This is using the deprecated password flow in OAuth, so that's another reason why you shouldn't do that. Yeah? But yeah, there's really no point in doing this. As I said, it's also not compatible with things like two-factor authentication and FIDO and so on and so forth. Yeah? You wouldn't believe how many discussions I had in my life with product owners that insist on having a native login dialog because, well, it's a native app, right? We want to be in control of every pixel on the screen. The other thing really that I don't like is that you are at the mercy of the quality of the developer, right? They should not store your password because they don't need it anymore. Well, hopefully they don't. They should store these tokens securely. Hopefully they do, right? If you have time, make an experiment. Do a backup of your iPhone, for example, right? And the iPhone backup has two parts, the application data and the keychain. Application data is application data, it's unprotected, and the keychain has all of your secrets. Now take a new phone and just restore back the application data. You should be logged out everywhere. Try that. If you are not logged out everywhere, some developer stores your secrets in the application data bucket, where it's completely unsecured. Yeah? It's easy to do. So yes, the easy answer is if you want to do authentication in a native client, use Code Flow with PKCE and open a browser. Done. Okay? You can reuse your existing login page with all of your security features, logging, auditing, fraud detection, blah, 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 what have you, okay? There's no point in creating another login page just because it must be pixelated, right? Open a browser, go to your login page, use Code Flow with PKCE, and there are different types of browsers. The preferred one is the system browser. Okay, so don't open a web view, for example, like opening a little browser without all of the browser things around. Use the system browser. You can inspect the URL. You can inspect the certificate if you want to. You can use password managers. And most importantly, you can share the cookie container with your system device, which might mean you already get single sign-on because you are already logged on to this token service in the browser, right? Basically, what you're doing is you're opening a tab of the system browser inside your application, and it behaves exactly like this. Single sign-on, less password typing, better user experience, less phishing, okay? You need to find a way how to get the data back from the browser to your app. Again, there are a couple of options here. The most secure one is what they call claimed HTTP URIs, HTTPS URIs, I should say. And the idea is this, right? You can register. So you've probably seen that, right? When you click on a link to Google Maps and you have the Google Maps app installed on your phone, and they don't open the browser, they open the app, right? Or with Amazon, for example. So the way this works is that on that URL that you're clicking, there's a little XML file which is signed by an Apple developer certificate that says, hey, if this app is installed on the phone, don't open the browser, open the app, right? And that's how you can get back data to locally installed apps from the web back. And that's the best way to do it. There are other options here. The spec has more detail, but my money is on the last one. Cool. Now, let's all get a little pessimistic. Let's talk about spas. You know, I did a workshop the last 2 days. You asked them, how many of you do spas? Almost everybody raises his hand, right? I mean, that's what people do. But it's also the most problematic type of client to secure because it's not the spa, it's not OAuth, it's not the token, it's the browser that's the problem, right? So there are a couple of attacks that only exist in browser-based applications, and they are because they live in a shared execution environment, right? You have multiple tabs open, multiple applications, multiple trustworthiness of applications, and you know they all start with cross-site request forgery, cross-site scripting, because one application is attacking another, right? So, you know, there are two fundamental ways to do API authentication in spas. The old style was with cookies. Cookies has the cross-site request forgery problem. The new style was access tokens, and you're basically swapping out cross-site request forgery with cross-site scripting. So you choose your poison, right? Interestingly, the only OAuth spec I ever read that says maybe you don't need to use OAuth is the OAuth browser-based application spec. Right? They say, you know, OAuth was made for cross-site scenarios, for third-party scenarios where you need to talk to third-party things or to, you know, maybe your application doesn't need that feature, but maybe your application runs on a site, right? And here's your front end, and here's your back end. What's the point of using tokens for that? Use cookies, right? You might have an authentication system that's totally fine. You might have to call external APIs, but if 90% of your architecture looks like this, then to be honest, to me, tokens look like overkill. Asking for them, managing them, keeping them alive, deleting them, storing them, and so on, yeah? But cookies just on their own won't cut it, right? Because cross-site request forgery. So we need some sort of anti-forgery protection here. And the good news is for all the people that knew that this is a problem but never changed their applications, the browser vendors will gonna fix you up now. Okay, there's this new thing called same-site cookies, where they by default isolate cookies on the site, okay? A site is not an origin. An origin is you know, protocol plus DNS name plus port. A site is basically everything that's under a top-level DNS registrar name, yeah, like api.mysite.com and app.mysite.com, they are the same site. Cookies will travel, but they won't travel beyond that, okay? The old way of doing that was anti-forgery tokens that required extra work, extra, you know, code to write. All of the modern browsers are switching to the same site model, and actually in 2 weeks' time, on the 4th of February, Chrome 80 will land. The free here doesn't mean anything good. Well, it does, but it's also bad. The free means that Chrome will change the behavior in Chrome 80, and all of the cookies by default will be same site. Okay? Before Chrome 80, you had to opt in to the same site protection with you know, Google, because hey, we are Google. They just changed that behavior. They changed the spec because guess what? The guy that writes the spec works for Google. So they will now treat every cookie by default with same-site protection. And you can only imagine how many applications will break on the 5th of February. Yeah? The even more nasty thing is that only Chrome is doing it like this. The others don't yet. Okay? So, yeah, the next, if you are building web applications, the next 9 months will be a mess. But it's for the greater good, I think. Okay, so ultimately, the OAuth BCP spec for web applications distinguishes between these two scenarios. You have an application with a backend and you have an application without a backend, and I just wanted to show you that great ASCII art again. I couldn't be bothered in turning that into PowerPoint things. But basically what they say is if you have a backend, all of your protocol handling should be done on the backend. You only protect the front-end, back-end connection with a same-site cookie or an anti-forgery cookie. And then all of the token-related things are happening on the server. If you have tokens at all, right? Maybe you don't need them at all. The only reason you had them is to talk to your own backend, and that might be overkill. The other scenario they call JavaScript applications without a backend. So apparently, and I never had that use case, but apparently there are applications which are completely deployed on CDNs with no backend whatsoever. Basically, you just download the JavaScript and they should work. Then you don't have the luxury of a backend, which means the only thing you can do really is do the token stuff on the front end. Okay? To be honest, this distinction doesn't make too much sense to me. They should really call it, do you want to store tokens in the browser or not? Right? Because that's the question you have to ask yourself. Do you want to store them in the browser? Then you use this approach. Do you want to store them on the server because you think that's better? Then use this approach. Yeah? They all have their pros and cons. None of them will save you from cross-site scripting, by the way, but that's a different story. Yeah? But the real question you have to ask yourself is, how do I store these tokens? Yeah? And as you know, whatever you use to store your token, it's not secure in JavaScript because it's available by JavaScript. And if somebody injects JavaScript in your app, they can access your data, right? So yeah, do CSP as good as you can. I know it's not straightforward, but try it. And not just say, let's turn it on, oh, it breaks, let's turn it off again next time. That's the wrong approach, okay? Refresh tokens in browsers, right? That's another really interesting topic now. Now that the browser world is switching to Code Flow with PKCE, refresh tokens are allowed. Should we use them? Refresh tokens have nice properties, right? They are long-lived, and they can be used to get new access tokens, which make them really nice for attackers, yeah? So, think carefully if you want to store refresh tokens in the browser, yeah? If you do, there are a couple of things you can do, like refresh token rotation, sliding expiration, replay detection, and so on and so forth, to make them more secure. I just wrote a blog post about that, actually on the way here at the airport. Or don't do refresh tokens at all, in the sense of that you're actually binding your renewal semantics to the session that you have with the server, and once the user logs out, the token cannot be renewed. Okay? Use short token lifetimes as well. That's another really good advice here. Okay, so what's next? So it turns out if you follow all of that advice, there are still attack scenarios here. Okay, so OAuth is moving into spaces where we didn't see that coming 8 years ago, like financial industry, healthcare, and so on, yeah? And of course, the more money is involved, the more motivated attackers get to find loopholes in your system, right? And that's a very, very good academic paper that shows more attacks that I haven't covered here that are not even in the OAuth BCPs, yeah? For example, there's an attack against PKCE. Wow. But the kind of like the summary of all of this is, we are pretty good these days if you follow the advice. There is one weak link, and that is still the browser. Okay? As I said, the browser is very powerful. It can show UI, it can follow redirects, yeah? But the browser is also very vulnerable because, hey, it shows UI, it follows redirects. So if you look at all of the specs that are currently in the pipeline, they all try to fix one thing, the initial authorization request, right? Where you send the parameters over the browser to the server. Because when somebody can tamper with them, they can do things that you might not expect can be done, okay? So actually the way we will go is we get rid of the authorization request the way we know it today. And you guess what? All of that together, this is being worked on now. OAuth 3, okay? And the idea is to compile all the problems and turn it into a new base spec that has all of these things covered. But as you know, the IETF is not like the fastest organization in the world. It will take many years. So people are actually working today on a thing called OAuth 2.1, right? And OAuth 2.1 is basically you apply OAuth, you apply the BCPs, and what you get in the end, that will be the new baseline, okay? No more implicit, no more password, use PKCE, all the things I just told you, okay? That will be, you know, it's not official yet, but I think that's what's going to happen, yeah? Two of the really interesting ingredients in 2.1 is, one is called secured authorization requests, right? I just said, this is the weakest link we have identified. It's happening in the browser. If somebody can tamper with them, we can play tricks on someone, yeah? So what if we could remove them all together? What if we could remove or replace all of these parameters with this? What's that? It's a JSON Web Token, right? That is, contains all the parameters as if they would be on the query string, but they are signed, and you can't change them. Okay? And guess what? They have a type. Yeah. That is an interesting idea, but practically speaking, these URLs get very, very long, depending on how much you put in these JSON Web Tokens. Yeah. So one step further is this. It's called pushed authorization requests. And the idea is, instead of doing an initial authorization request, you first open a back channel to the server. Then you push all of your parameters on that back channel to the server. No browser is involved so far. Okay? This call is authenticated with the client ID and the client secret, and you can make that as strong as you want. Okay? So we're pushing these things first on the back channel. What this will give us back is basically an identifier for the pushed parameters. Okay? And then you are opening the browser, and all you put on the authorize request is the identifier. Okay? So now on the server side, we will basically reach into our data store. We will resolve the identifier to the parameters that have been pushed before by, authenticated pushed, and then we will do the authorize request. Okay? And that's all being done, as I said, to get rid of these unverifiable parameters on the front channel. I think with that, it's pretty cool. I can't wait to implement that. Okay, so summary. You might think now, why would I bother with OAuth at all? It seems to be completely insecure, right? I mean, so many things are going this and that, and I have to do this, and if I forget this, then this is happening. I guess the answer is, it's hard. It's a hard problem to solve, right? OAuth 2.0 was the first iteration of that protocol. We learned our lessons, and I'm not saying it's insecure. I'm just saying we can do better, right? And I'm also saying that still the most problems we see are implementation flaws and not protocol flaws, yeah? The thing is this. There are some things you can't mitigate as a developer. There are some things that are easy to mitigate, right? And some things will always stay hard, regardless how hardened the protocols are. If somebody does a targeted attack against your system, it will always be hard because they analyze your exact implementation and not just the general thing, right? Still, people ask me, should I use OAuth at all, or should I do my own protocol? And the answer is very easy. Don't. Okay, what a specification really is, it's a pre-vetted threat model. Many smart people have worked on creating the spec. Many smart people have tried to break that spec. And many smart people are still iterating on it, and we're getting improvements. If you write your own protocol, there's exactly only one smart person that worked on it. There's also exactly only one smart person that tried to break it, right? So what's better, right? So yes, I think OAuth is here to stay, and it will improve and it will get better, but we are pretty good. Thank you.